Can I? Hello. Okay, that sounds good. All right. Can you hear me now? Ooh, excellent. Sounds like people can hear me. Wow, look at all these joints. Oh my God, that's incredible. Okay, welcome. I am going to go through independent dependent probability. Ooh, I guess I should have looked at these problems first. I just copied them and started to go. All right, well, we'll figure it out as we go. So, we are looking at telling whether events are independent or dependent. Explain. All right, so what we talk about, there are two different types. We are talking about independent events, and we are talking about dependent events, okay? So the difference between these two things is when we look at independent events, they cannot connect or have any effect on the outcome of the situation. So if I flip a coin and I get heads and I roll a die and I get a 1, okay? Here's a 2. And I get a 1. These two things have no effect on the other. Like whether I flip a heads or a tails here and whether I roll a 1 through a 6 here, there's no effect of the outcome on one versus the other, okay? So what does that mean? Well, if we were to pull a card out of a deck of 52 cards, okay, and I'm looking, it doesn't matter. If I pull any card out of here, like the Queen of Hearts, okay, if I pull the Queen of Hearts out and then I pull another card out of this deck, I have just changed the probability of this event, because the first event is something out of 52 cards. But once I take a card out, now it's not 52 anymore. It's only 51 because I already took that card out. Unless I put that card back, and it has to specifically state that you are putting that card back in order for it to be independent events. If I take a card out and I take another card out, those are dependent events, and those will affect the outcome of my probability. So when we look at these situations, you really have to think about whether they're independent or they're dependent. So if I flip heads on a coin and tails on another coin, so I flip heads on this and then I flip tails on that, is one affecting the other, okay? So if we talked about this in class the other day, let's say I've got a lovely bunch of coconut, I have a box of chocolates, okay? And I've got milk chocolate, I've got dark chocolate, and I've got white chocolate. Milk chocolate, dark chocolate, white chocolate. If I eat one of those, when I eat one of those, I'm going to eat a dark chocolate, do I have 6 chocolates in there anymore? No, I only have 5. So in that case, I have just changed the probability and it becomes dependent when that happens. If I flip this coin and I get heads, and then I flip this coin and I get tails, these are kind of they have no connection with each other. So I can independently flip these. So this is an independent event. And explain? Well, flipping the first coin has no effect. Flipping the first has no... Oh man, we talk about this all the time too. Oh God. I'm going to go effect, but I think it's affect. We talk about this all the time in my classroom. Like, is it effective or affective? And supposedly if it, I'm terrible with, and I always question this one, but I'm going to put effect, although I bet it's affect. So flipping the first has no effect on the second coin, okay? So if it has no effect on the second coin, this is what we call an independent event. Okay, so that's our first question. Number 2, 2 number cubes, one red, one blue, are rolled. First off, that should be an indicator to you. If I have a number cube, and yes, in math we call them number cubes instead of dice. I don't know why that is, but that's the case. And they called one of them red. Okay, so we're gonna red this one. So there's our red one. And then we have another one that's blue. All right, so let's draw our blue one. Okay. And we'll do this. Okay, and then this one is going to be our blue one. All right. Now, 2 number cubes, one red, one blue, are rolled. What is the probability that the outcome on the red number cube is even and the outcome on the blue number cube is 5? Ooh, all right. Now, once again, are we dealing with independent or dependent probabilities? It's going to make a difference, because if we're looking for the probability of A and B happening, if it's independent, it's just the probability of A times the probability of B. But if it's dependent and we want the probability of A and B, we are going to have the probability of, let me think about this for a second, sorry. So that would be the probability of A times the probability of B times the probability of A given B. I do not want to say this wrong, so let me look it up real quick before I give any false information. Sorry. But it's the complexity of probability, and those simple little tiny things that can happen can ruin the rest of your day, especially with probability. So dependent events, I want the probability of A and B, so that's going to equal the probability of B given A times the probability of A. Okay, so this is the probability of B given A times the probability of A. And once again, I wanted to make sure, because it is very sensitive and probability is difficult for that specific reason. Like those little idiosyncrasies, those little nuances can really affect your outcome. So making sure you have those properly done is very important. Oh, you can't see that over there. Let's see if I can maybe drag all of this group. Okay. And show that here. Okay. So we have independent and dependent. All right. So now when we look at this, once again, these are independent situations. So I would have been okay either way by just doing the probability of each. But when we do the, oops, don't move. Yikes. When we do the probability of anything, remember, it's going to be desired over total. And that goes back to our original probability stuff that we worked on a while ago. But it's always going to be your desired over total. So when we look at the probability of a red, okay, a red cube is even, we have to think about this red cube. How many even sides are on this? And if you think about a number cube or a dice, there is 6 sides to it. There's 1, 2, 3, 4, 5, 6. Each one is labeled as 1, 2, 3, 4, counting the dots. So in this situation, when we count the evens, we have a 2, we have a 4, and we have a 6. So there are 3 total outcomes that are even. Each opposite equals 7. Canada versus States. All right. Thanks, Mom. And we have 3 even numbers out of our total, which is going to be 6 sides. Okay? Now, you can simplify this beforehand or after. Doesn't really matter. But when we simplify, it's going to be 1 times 3. It's going to be 2 times 3. The 3's are what I like to call oneing out, because 3 divided by 3 is a 1. And if you take 1 and times it by anything, you're going to get the outcome that you multiplied by. 7 times 1, you're going to get a 7. 8 times 1, you're going to get an 8. So that 1, it really doesn't affect our problem. It affects the way it looks, because 3 over 6 definitely looks different than 1 over 2. But when you simplify it, it's like cutting a pizza. I could cut it into halves, or I could cut those halves into halves and make 3/6 out of it. So it just depends on how you look at these. So the probability of the red die, we've got 1/2, and then the outcome of the blue cube is just rolling a 5. So let's do the probability of the blue one. Well, out of this, how many 5s do we have? We've got 1 5. So we have 1 out of 6 different sides. Okay. So if we take, and we want the probability of A and B happening, we want both of these things to happen. But they are independent events, so that's going to take 1/2 and multiply it by 1/6, because we're going to do the probability of A times the probability of B. And then just multiply straight across. So 1 times 1 is 1. 2 times 6 is 12, and this is simplest form. If we wanted to, once again, we like to convert ours into decimals. We have 0.083. Oops, sorry. So this is 0.083. And if we times it by 100, or we move the decimal place 2 places to the right, we get 8.3. And that's our percentage that we get. So there's an 8.3% chance of this outcome actually happening. I don't know why this is more interesting than work, but it is. Well, good. I'm glad. And probability is difficult, man. It's fun. And you can manipulate these problems so many different ways, and it really gets tricky. So really kind of paying attention to what the question's giving you, how it's asked, is really important when it comes to probability. So there are 6 black socks, 4 white socks in a drawer. If one sock is taken out without looking, and then a second one is taken out, ooh, bells should be going off right now. This is dependent probability. Okay, we need to make sure and take, if we want A and B happening, we have to take the probability of A times the probability of B, given that A happened. Okay, that's starting to make a little sense. All right, that's coming back to me. So we want the probability of B, but it's given that A actually happened. So when we look at the probability of A, what is the first thing we want to have happen in this? What is the probability they both will be black? So the first thing we want is A to be black. All right, I got back to work. Got to get free healthcare to my fellow Canucks. Awesome. Well, have fun, Mo. Are we on for tomorrow night, though? That's the real question. Probability of B given A. So for this one, we want the probability of a second black sock, knowing that the first was black. So it's given that the first is black. All right. So first things first, we want to find what is the probability of A. So if we were to choose what is the probability of A, we want to know how many black socks there are, because remember, we want the probability of anything is going to be desired over total, right? So our desired outcome is a black sock. So we want black over total. So how many black socks are there? There are 6 black socks. Out of how many in the drawer? There are 10 out of that drawer. Okay? Now, let's go to the next piece of this, because this is where the understanding is going to take place. And where independent, dependent just differ from regular probability. So now we want to draw a second black sock out of the total, with the first being a black sock. Okay, so if we pull the first thing, what is the first thing that happens? We pull the black sock. So how many black socks are left? If we pull, then the first pull was a black sock. Well, it stands to figure that if we started with 6 and we pulled one, we would only have 5 black socks left. Okay, hopefully that makes sense. And what is the total with the first sock already being pulled? Now, this is once again where you got to follow. And if you ever put dependent probability, you should know your total is going to change. Because you're doing something and then you're doing something else. I'm eating a piece of chocolate, and now I'm eating a second piece of chocolate. Well, if I already ate the first one, my box is going to have one less in it. If I pull a card out of a deck and then I pull another card out of the deck, these are dependent things that are happening. So the total number of cards when I pull the first one is going to be different than the total number of cards when I pull the second one. It's just, that's what dependent probability, that's why we need it. That's why it's important, because we are starting to change the total every time we do this. So if we want the probability of A and B happening, we need the probability of A, and then we're going to times it by the probability of B given that A happened. All right. So with that, the probability of A is going to be, I wonder if I should line it up. I don't know, spitballing here. I think I would prefer for my organization that I line it up under. So you know P of A is 6 over 10 times P of B given A is going to be 5 over 9. Once again, I'm not sure how you learned fractions, and maybe you still struggle with them, but you can simplify this in a matter of speaking, where we could convert 6 to 2 times 3 times 5, right? 2 times 3 gives me 6 times 5. And we could also do 5 times 2 times 3 times 3. And the reason we can do that is 5 times 2 is 10, and then 3 times 3 is 9. And if we highlight something on the top and something on the bottom and something on the top and something on the bottom and something on the top and something on the bottom, if they're the same, these all one each other out. Well, if that's the case, then the only thing left up here is a 1. And then the only thing left on the bottom is a 3. So it should stand to figure that this answer would come out to be 1/3. Now, you can trust or not, but let's go back here and test it out. So 6 over 10, and then we're going to do a times, and then we're going to do, I forget the other fraction, 5 over 9. 5 over 9. And once we do that, it will show us that we get 1/3, or 0.3 repeated. So we have our 1/3. We know it is 0.333 repeated. And if we times this by 100, which is moving the decimal 2 places to the right, we're going to get 33.3%. So there's a 33% chance of pulling a black sock and then another black sock, which hopefully stands to figure because there are more black socks than there are white socks, and there's only 10 of them total. So hopefully it sort of begs the question that 33% chance is a pretty good one. We should be able to do this once every 3 tries. Oh, man. Thank you, Ye the Rapper. I appreciate the like. It should beg to differ that you should be able to do it 1 out of 3 times, where I pull a black and I pull a black, and I pull a black and I pull a white, or I pull a white and then I just start all over. So 1 out of 3, we should get black, black for our socks. Okay, so teacher of a class that contains 12 boys and 16 girls needs to pick 2 volunteers. She randomly selects 1 student, then selects another student from the class. Find the probability. So think about this. If I pick 1 student out of the total, isn't that going to lessen my total by 1 because I selected that student? If I want 2 volunteers, I can't pick the same person twice. That doesn't make sense. Because if I pick, who do I want to pick? I want to pick Kendrick. If I pick Kendrick out of this pile, and then I pick Kendrick again, that's only 1 volunteer. So I can't pick Kendrick twice. So I have to go to Kendrick, then Anasia, or Samaya and Corey. Like, my students could be like, oh man, you used my name. It's okay. I mean, I didn't use any students' names. All right. So this is definitely a dependent situation. So if I want A and B, I need the probability of A, and then the probability, that should be a P, the probability of B given A happened. All right. So the first thing that we want to choose is a girl, then a boy. So we want the probability of a girl, then we want the probability of a boy, given that a girl was drawn. Okay? So if that's our situation, so we want probability of a girl and a boy, we are going to do the probability of a girl. And I keep writing it as I'm going to make a big long line. And I don't like that. I think organizationally, especially when we're trying to understand what's going on, I would keep them vertically so that I can see P of G, what it becomes. And how many girls are there? Remember, desired over total, there are 16 girls out of 28 total students. Okay? Now, here is the thing. If I pick a girl for the first individual, did I affect the boys at all? And hopefully in your mind, you're ringing, no, you didn't do anything with the boys. And that's good because they're still there as 12 boys. But I did pick 1 student. So this 28 now becomes a 27. And that's really the key of dependent probability, is knowing that this total has to change. It really does. All right, so we're going to do 16 times 12 on top. And we're going to do 28 times 27 on the bottom. And I am not going to do that. So we have 16 over 28. And it's really for time's sake that I'm doing this. I could do this out and show you. But I also want to get to bed. But I needed to get this done for tomorrow so that they have it for their class. So, all right, so we're going to get 16 over 63. 16 over 63, which is 0.25, and we're going to put 4. 0.254. 54. Oh, and once again, I'm going to go back to, there's not a lot of times when you are looking for probability. There are times, especially in betting, in the real world situations, I'll say. In the mathematical situations for probability, if you're ever given a probability question, don't pick anything that's over 100. Chances are, for the most part, 99% of the time, when you're looking for a percentage, it's going to be under 100%. So if you're looking for a probability, err on the side of it's probably going to be the one that is under 100%. There's going to be few cases where that's not the case, but more often than not, if you get something over 100%, which means 1 point something or 5, anything greater than 0 point something, double check your math. Please go back and look, because if you get anything other than 0 point something and we're working with probability, chances are you got something flipped around. All right. So we got a 25% chance of that happening. Now, she chooses 2 boys. So let's talk about a boy and a boy. So we have the probability of a boy times the probability of a boy given that a boy was chosen. So the probability of a boy and a boy, we are going to take the first boy, so there are 12 out of our class of 28. But once we choose one boy, there's only 11 boys left. And once we choose one student, now there's only 27 students left. So making sure that we account for that in our dependent probability, okay, is very important. So we're going to do 12 over 28. 12 over 28 times, oops, that is not what I want to do, times 11 over 27. And because remember, we went down on both of those by 1. So there's a 17.4, 17.5. 11 over 63 is our answer. 11 over 63. 63. And what was it? 17.4? Yeah, 17.5 because we round. 17.5 times it by 100, which will move it 2 spots. 17.5% is what our answer would be. And that makes sense because there are less boys in the classroom. So choosing 2 boys, obviously the probability would go down than if one of those was a girl, because there are more girls in the class. That's a higher probability of choosing a girl in the class, just because there's more options. If you put G's in a bag and you put B's in a bag and you drew out of there, there are more G's that I can choose from. So that should be a higher probability. So even thinking along those logistical things, does that make sense? So keep that in mind when you're comparing these answers. All right, last one. Now this 24, I counted it. I counted the first time and I used this one and I got back to that one and I couldn't remember if I counted it or not. But I counted this like 3 times and I know there's 24. But we're going to start on here at A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4. So I promise you, I counted it. I wanted to make sure. So there are 24. Okay. You're playing a game that involves spinning the money wheel shown. During your turn, you get to spin the wheel twice. Okay. Hopefully this is ringing in your ear. If I spin this, what is the probability you get more than 500 on your first spin and then go bankrupt on your second spin? Okay. So when we are doing this, it could have been dependent probability if they had a question where what is the probability that your 2 spins would add to more than something? Because the first spin is going to be, or the second spin and the first spin are going to be dependent on each other. Like if I roll a 500 on the first spin, I'm going to need more money for the second spin. So that's where dependent could cross these lines, but this is an independent event. I want the probability of A and the probability of B. So I need to find the probability of A, and the probability of A being that you get more than 500. So more than 500. Okay, then we need the probability of B given that A happened. So what's the probability of B given A happened? Bankrupt. So we're bankrupt. Given that we got more than 500 after our first spin. So, my wonderful student teacher already labeled the ones that were greater than 500 for my students. So, beautiful. So all they would have to focus on is how many A's are there. So I have 1, 2, 3, 4, 5, 6, 7, 8. Let's just to double check. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 scenarios out of, remember, we have 24 spaces. Okay. Now, just because we landed on one of those doesn't mean that it disappears. It's still there, even when we spin it. So when we do this one, because it's independent probability, my total isn't going to change. I still have 24 spaces on this wheel. But how many of them are bankrupts? Well, we can see there are 2 B's that she wrote down. So there are 2 situations where you can go bankrupt. So in this scenario, if I want the probability of A and B, that's going to be the probability of A times the probability of B given that A happened. Excuse me. So we have the probability of A and B. So probability of A is 8 over 24 times the probability of B given A happened. So probability that we landed on a bankrupt given that our first roll was more than our first spin was more than 500 bucks. So that's 2 out of 24. Now, I could have simplified this to 1 over 12 because I can divide the top and the bottom by 2. I can divide the top and the bottom by 8, 1 over 3, and then get my answer. Or I can go through the same scenario we did. So let's look at this 1 over 3, because isn't 8 times 3 going to be 24? 25, 26, 27. I think that evens out. So I could do 1 times 8 and 3 times 8, and the 8s one each other out. And I can do 1 times 2, and I can do 12 times 2, and the 2s one each other out. So I'm left with that. So it begs the question, hopefully I get 1 over 36 when I do this. So 8 out of 24 times 2 out of 24, because my denominator didn't change in independent probability. And I get 1 out of 36. Hey, I did it right. Sometimes, you never know. So 0.28. So then this becomes 0.28 times it by 100. We're going to move it 2 spots, and we get 2.8%. All right. Well, this is independent dependent probability. I hope you enjoyed our lesson. If I need, like and subscribe, join, I don't know, follow. I'm looking to get up to 10,000 viewers for some reason or another. I'm just trying to promote my business. I would love to tutor through the internet, through the powers that be, make a little extra coin. Teachers are broke. We don't get paid enough. So looking for those side hustles. This is being one of them. So if you want to tutor, please join the Discord channel in my bio link. And yeah, tell you all the information you need to know. Have a blessed night. Have a great week. And I'll see you next time.